Can you hear me? Okay, cool. So, come with us now on a journey through trigonometry and oscillation to the world of the fragment shader. So hi, I'm Lisa. And I hope that at least some of you are familiar with the British television show The Mighty Boosh. Otherwise, this might have seemed really, really weird, but yeah. As Saskia said, I'm Lisa. I am listless on a lot of parts on the internet if you're looking for code or my website or whatever. I work at a German nonprofit called Open Knowledge Foundation Germany, where we do a lot of things around open data, governmental transparency, freedom of information, where I do a lot of technical things, I would say. But in my free time, I mostly do, or concern myself with making video games and also creative coding in all sorts of sorts and of all sorts of shapes, because it's a really interesting field if you're web development is nice, but there is so much more you can do with computers. And this is exactly what brought me here today, is the creative coding part, and also a little bit the Mighty Boosh, because the television show made me realize that it's sometimes you need to learn a lot of things in order for you to appreciate other things. So for the Mighty Boosh, I had to learn to understand thick British accents and British humor. It was not easy for me. For the part of creative coding that we were going to look at today, you had to understand, and I had to understand and learn a lot of things that I had never had exposure to. But now that I know a little bit about it, I can appreciate all the more. I was talking about fragment shaders, and I want to start simple with what is a shader? And a shader is simply a program that runs on your graphics card or your GPU. Simple as that. And you might be wondering, well, what's so special? Code runs also on the CPU, your central processing unit. Why should I care? The cool thing is that shaders are really strange programs because they need to run highly in a highly parallel environment, and they're stateless. So if you write your usual code and it runs on the CPU, you have maybe 4 or maybe 8 cores. That is the maximum of parallel things you can do in your program. But usually your CPU is made for doing things in a sequence and with a lot of logic, which is what day-to-day programs usually concern themselves with. But in the shader world, in the graphics world, we can't do a lot of logic, we can just do math. And we need to do it as fast as possible and as parallel as possible, because shader is a program that runs for every single pixel on your screen 60 times per second. So we need to be fast, and we do just chuck out all the pixels, or all the computation for the pixels that we need. So you can think of it as having hundreds, or actually thousands of threads running on your graphics card, running the same code, and deciding what to render to your screen. And this is an environment where we can just not know what is happening around us. We just have the information that we have for every single pixel. What I also for the rest of this talk, I will probably use the word shader when I actually mean fragment shader, which is a specific kind of shader. And to understand this, why it is specific, we need to talk a little bit about the graphics pipeline. And the graphics pipeline is, first of all, a conceptual model that lives in your computational devices or anything that has a screen, really, helps conceptualize how to display a 3D thing on a 2D screen. And this might sound really trivial, but actually, if you have to think about it, somebody had to came up with the math to decide how does this actually work math-wise, that things appear on a 2D screen when they should appear as a 3D object. So this is the graphics pipeline I was talking about. So in the beginning, you have a bunch of points in a thought of 3D space that then runs through different steps along this pipeline. We get shapes, we get they will be cut into triangles. The interesting part, I think, is then the rasterizer. This is when the step decides okay, we kind of know what will happen in this virtual 3D space, but then we need to decide what pixel should should take over which part of this thought of thing. And what we will concern ourselves with is this part here, which is the fragment shader, which is we know what pixel will do what kind of information for us, but then we need to give each pixel a color. And then in the end, something will happen on our screen. Right. So the only thing that is actually really important about this for you is fragment shaders are all about telling each pixel what color to display. Cool. So this is like graphics pipeline. It's like a mental model or like a conceptual model, and how do we interact with this like actually? And since we're dealing with like very low-level hardware stuff at this point, like things that run on your graphics card, like really, really low level, really, really fast, there are several like abstraction layers on top of that, or like interfaces that we can use. A very, very popular one is OpenGL, which is the Open Graphics Library, which comes with its own language, GLSL, the OpenGL shader language. Other like graphics libraries or like interfaces are out there. For example, you may have heard of Vulkan, which is like the hot new kid on the block. So maybe like in 2 years, I'll be talking about Vulkan instead. But OpenGL is pretty much the standard right now. Quickly about GLSL, which will be the main focus point of all the code examples that follow later. And it's not a Lisp, and it's definitely not Clojure, and it's also not functional. It's a C-like language, so lots of curly braces, semicolons, static typing, all the things that that I actually like. And GLSL has a lot of cool and built-in functions all around math, because this is what we do. We don't have logic, we can just do math. And we have a lot of interesting features around vector manipulation and matrix math, I would say, that are really interesting. If you're interested, come talk to me later about swizzling, which is such a cool concept. But yeah, I don't have time to do anything else about this, but tease you with it. Okay, can we write shaders in Clojure? And I was like, yeah, we're doing like, this is the Clojure conference, and we want to do some like visual shader programming, and like how can we have sort of like a little interactive thingy that I can show you like why shaders are cool, but that also you can see something and learn something at the same time. So I wanted to write a shader context thing in Clojure, but the shaders themselves will be written in GLSL. Well, the first point is pick a library, I guess. So I was looking out into Clojure land and see like what sort of like shader-related things are out there that I could use to build a little like demo app for you. There's a shader graph by Carsten Schmidt, which it's not just like a library; it's a dependency framework for shaders, and I think that's already saying quite a lot that. That this library is massive. It has probably everything you ever want to do, or that you will ever need if you want to do like a proper graphics thing. From like the vertex shaders, so like dealing with the math of the shapes that you might want to display, and also like the fragment shader part. But I was honestly a little bit intimidated by what all the things it could do, and I was like, I don't even know what all of these things are. So I was looking for something similar, like smaller and simpler. I also stumbled upon shader tone, which comes from the overtone people, which is the visualization library that goes with overtone, so you can like easily visualize the music that you're live coding with a live coding shader. So I have some examples of Joseph Wilk and Ripple Electric later, which use just that. So it's all fragment shaders. But generally, every Java game engine that allows you to write custom shaders can be used to interact with the graphics pipeline. The thing is, I'm not a Java person, and I think Java is scary, so I was looking for something else. So this is where we like quickly dip into WebGL. So WebGL, what is WebGL? WebGL is basically, just like OpenGL, an abstraction for the graphics pipeline, but it lives in your browser. So it's your browser's API or like way of talking directly to the graphics pipeline on your machine. So you write something in the browser context, and the browser forwards it to your graphics card. We can all do all the fast math that we need, and then like put it back and have a nice image or whatever we're coding to display. So browserland, this is where I come from. JavaScript, it's an environment I feel much more comfortable with, and like incorporating it into my app. And is well, JavaScript is a vast ecosystem, so you can basically just pick your level of abstraction that you would like to have, and then go for a library around this. For example, there's Pixie.js, which is a really popular one that a lot of JavaScript game engines use for their WebGL rendering. But in this case, I went for a package called GLSL Canvas, which is written by Patricio Gonzalez Vivo, and now there was feedback. Okay, which is also a creative coder. And he does a lot of like work with fragment shaders. He wrote the book of shaders, which is where I learned everything that I know about shaders from. And he wrote this simple tool, and it's basically just have an HTML canvas and put a fragment shader into it. Done. I was like, yes, that's cool, because I don't want to set up the context. So it's a nice level of abstraction that I wanted to have. And the thing that I made is called figfrag. Its name is a joint thing because I used figwheel main for the amazing browser REPL, and this GLSL canvas to put the fragment shader in there. And we're going to take a quick look. I have to see how this works. Microphone stand. Oh my god. Yeah. Okay. So it looks like this. You see nothing, because nothing is happening right now. But basically everything here is the canvas that I'm using, and later on, here's a little interface for you that will show you the shader that I'm sending into this canvas, and then also the values and uniforms that I will add on top of that. This does not have to make sense right now. It will in a second, just so you know. Okay. Finally, let's write a fragment shader. Woo. You can kind of not read this on the black highlighting, but that is okay. But this is where figfrag comes into action. So I'm on my computer. I'm using the browser REPL so that you don't have to see me code, which is really awkward. Right. Boom. Okay. So you can actually not see anything. That is okay. So what is happening here is, where's my mouse? Okay. Is that this is the program that is currently running. You can kind of, and we'll toggle this back. There is a gradient. I promise it is there. I can see it on the screen. It says, okay. So what is happening here is that this is the shader program that is causing this gradient. And what we do is this in our main function. So this is the entire program that runs for every single pixel on this canvas. And this is kind of like everything that it does. So we get a magical variable that is called GL_fragchord, which is sort of a variable that OpenGL sets for us, which contains the current position of the pixel that we are working in. So for each pixel in our canvas, X and Y will be different. This is called a varying because the value varies for every pixel in our program. And then we have something called uResolution, which is defined here as a uniform. And uniforms are special because they are values that are sent from the central processing unit into our graphics card shader. So we can kind of like inject more information into our like little graphics program. What we're doing here is that we're kind of like normalizing the our coordinate space, so we get something like a nice canvas between 0 and 1 instead of like whatever actual resolution we're dealing with, so we can kind of like port this very easily. And then we're also setting a magical variable called GL_fragColor, and we set this to like a color value. And this is kind of like the entire point of the shader is setting this variable to a color that will then be displayed. I can also do, so this is the color in this case, you possibly have thought of that a four-dimensional vector in this case is RGB plus an alpha value. In this case, I'm not doing anything with the blue value here, but I could, and I would do so in my little live coding thing, because we can also pull in other uniforms that give us other information. I'm gonna write a simple thing here. So what I did now is that you will see that it will like kind of maybe change colors over time. Yeah, you can see a little bit of difference. Is that I pulled in another uniform called uTime, which is just a float that will be the time that has passed since the program started running. And on the blue channel, I now say that like, okay, I use the sign of uTime. So like we will increase and decrease the blue channel value as long as this like runs, and we get this like, yeah, nice little visual effect. Okay, that was example one. And this is basically, this is all that like shaders are actually about. Like we have some coordinates and we do something with it. And this is probably the most functional slide in this entire presentation. And it's also like never mentioned anywhere in graphics or shader programming, but I thought it was really, it was easier for me to reason about a shader if I thought of it as like a deterministic function, even though the main did not take any arguments or returned anything. But what we really have is an input, the coordinates in whatever uniforms we're sending into the shader. And for these inputs, we will always generate this like this output of the color, and we can do this in a vastly parallel and like yeah, cool way. So yeah, this is my take on graphics programming. It's actually functional programming. So anyway, let's draw some more. Let's draw some cool stuff. And I think now that we kind of know what to do, or like how we can create a shader, we have sort of like an environment. We can start getting nitty-gritty with math and all kinds of other cool things that we can use to create visual effects. And this is where I would enter oscillation. Oscillation, heart of Clojure, oscillation. Oscillation is the periodic movement between 2 points. We have cool properties like amplitude, which is the distance from the center to either of these extremes. We have the period, which is the amount of time it takes to complete a cycle in this like oscillation motion, and the frequency, which is the number of cycles per time unit. If this is physics for you, yes, it is. It's awesome. We already like saw a little function that I used to yeah, have the blue channel oscillate in a sense, which is the sine wave. So the movement of the blue channel in the earlier example was based on sine. And sine is really cool because it's a continuous, smooth periodic oscillation. So we get nice interpolation between like 0 and 1 or -1 and 1 in this case. It is also the graph of the sine function. So it's basically a function, but if we map it, we get like also like a nice wave. And it has so many, like it appears everywhere in math, in physics, in signal processing, in like various parts of engineering, and it's kind of like fascinating how sine is just always there. So I thought it's a cool candidate to like draw it in a fragment shader. And because you can probably see this better in FrigFrag, I will just go back. Actually, for you. Okay, so what we're seeing is a sine wave. Nice. I skewed it a little bit so that because it's we're still dealing with a 0 to 1 coordinate system here, so I made it a little bit smaller so we get like see the oscillation a little bit more. But the only thing that actually matters here is this line. This is where we assign the value of the y-axis, so like where on the y-axis a certain thing should go, and we take the x value in there in our little sine function, and then we just like throw in some numbers to make it look nice. And you will see later that this is easily we can substitute these for uniforms that we send into the shader to like do stuff with it. And I have something prepared as well. Okay. So what is happening now is, I pulled in more uniforms, u time and also u mouse, which is the coordinates of the mouse in the space. And then I kind of what was hard-coded before, so I chose to use the y position of the mouse for the amplitude of the sine wave. And I also added time so that it like keeps on moving because the value is ever increasing. And the x value is sort of for the frequency. So if I like, so I have, no wait, the other way around I think. X is x is the amplitude and y is the period actually. Yeah. So we can do stuff with this. Like we could, yeah, it's kind of fun. Like basically, no, cool. And you can also like throw in more variables to like have it like just oscillate faster, or then like put in some like more colors. This is just like one color, but I think you get the gist. It's a lot of fun. I'm already enjoying it. Okay. So this is one thing that we could draw, but it's also, I think, interesting to see what others are drawing with WebGL. And I also mentioned Ripple Electric earlier, so Joseph Wilkes' live music coding alter ego, and he also draws visualizations with fragment shaders. They look like this. So like there's like a black thing in the middle and red around, and it's like wobbly. It's super cool. There's more like starry sky. You can also like circly-ish around the center, and there's like this example, which is also circles around the center. And I thought maybe we should draw circles around the center because that seems hip. That seems cool. These are usually known as polar shapes. So they revolve around a pole. It's actually not so easy to draw polar shapes because if you're wondering like, okay, but how do we only have like x and y coordinates, and then we need to like put them on a circle. Okay. So what we need to do in order for us to draw polar shapes is that we need to switch the coordinate system. Because the usual coordinate system that we deal with is the Cartesian system. It's named after French mathematician René Descartes. And yeah, we have x and y coordinates to describe a point, which are the components of our vectors. The polar system, on the other hand, is named after the points where the rotation axes of a body intersect with its surface, like the North and South Pole. I know. Using the angle of rotation and the origin of the pole, we can use to describe a point. So we have, wow, this is like faces that don't know anything what's happening. Okay, so we have an origin of our pole, and then we describe a point by the distance to that pole and the rotation angle around it. Usually using radians, but we don't have time to go into radians, so yeah. This will all make sense in a second, I hope, because how do we get like direction and rotation of an angle is like all we have is like x and y like as a little vector in our program, but these map directly to the direction and magnitude of a vector, and all we need to do is convert between x and y and magnitude and direction. And this is where I can introduce you trigonometry, heart of Clojure, trigonometry. And trigonometry is the math of right angles. And it's everything we need to switch between coordinate systems. So this is, I hope you feel like school again. So this is a right triangle. And we have some like nice formulas that trigonometry has in store for us. Well, apparently it's called SOHCAHTOA. It's a little like bridge to help you remember these formulas. Because they help us describe, or like our formulas that allow us to calculate this angle in a triangle with our friend sine and like its friends cosine and tangent. And especially tangent will be interesting for us. So the tangent of an angle is the opposite divided by the adjacent. Because if I now switch this right triangle and like name its sides differently, so we have x and y, this is also like the components of our vector, then the hypotenuse would be the magnitude of our vector, and then all we need is the angle. Magnitude, or the length of a vector, there's a built-in function for this, so we don't need to concern ourselves with that. But to solve for the angle, we can use arctangent. So like tangent of an angle equals y divided by x, and then to get the angle out of there, or like to solve for the angle, we can use arctangent, or atan, as in most programming environments. So we get the angle with atan, And this is all we need to like then, so we have the radius and the angle, and then we can draw polar shapes. Let's draw a polar sine wave, so I really hope this makes sense to you. I will just copy this. Okay. So, this is the sine wave drawn in the polar coordinate system. And the only thing that is different from before is that here we calculate like the radius and the angle, and then we just say like, hey, f is sine, and then like I increase the period, so we get like 3 periods in the thing. And this is pretty cool, I think, because this shape looks really, really cool. So now, because I'm actually probably out of time. Yeah, exactly. I'm going to take a few more minutes. I'm sorry. Also, maybe a little epilepsy warning, because this might get a little bit funky for the last demo. Okay. So what's happening here is that before the examples, I was only using one color channel, and the other ones were muted. In this case, I used different oscillations for the different color channels, but also I oscillate over the alpha value. This is like when also like the black to white switch happens. And now we come to the point where this little uniform thing down here becomes interesting, because I can also I have set a uniform up here, which is a 4-dimensional vector, which I just called u vars. So this is something that I made up. And the u vars is, if it's not set, it's just 0. And this is why we deal with circles here and not with anything else. And what I'm going to do now is send in more values into the shader uniform. That will then take its place in the program and do cool stuff with it. Maybe the hardest part is thinking of random numbers. Wow. And a typo. Okay. Okay. So you can see down here what numbers I sent into the shader. So 5, 8, 8, and 3. And these map now to the various parts of this shader. I also have some like mouse interaction in there. So basically, it's about the how they oscillate and like the amount of like flower petals that you're getting. But this is like now the numbers are very close together. But you could also say maybe let's do 50, 80, 80 or something, and then you get like really weird, like super fine and grainy like other things, and you could like totally have this in like a psychedelic, I don't know, visual installation at a concert or something. And then like for the values that I'm sending in right now, they're like very random and handpicked, but instead of like just having a vector of numbers, you could also say you want to send in something that is called a texture, which is just like more information. And what shader tone, for example, does, it's very closely connected to overtone. So overtone sends the Fourier transformation of the music that you're creating directly into the shader as a texture, so you can have or like do visualizations literally based on the music. But this is like you could connect anything to this, like maybe like an external keyboard or something, and then just pick up whatever signal you want, package it in a uniform, and send it into this, and have fun with it. Okay. Yeah, we already did that. This brings me to the recap part, and this is going to be fast because I'm already over time. Shaders are stateless parallel programs running on your graphics card. OpenGL or WebGL are APIs to talk to the graphics pipeline. GLSL is the programming language that you will use your shaders for. Fragment shaders get sort of an input from varyings, like the coordinates of each pixel, and uniforms, and in the end output a color. Uniforms are the coolest thing because they are values that you can calculate on your CPU and then send them to the graphics card for further computation. Trigonometry is right angles, and the trigonometric functions sine, cosine, and tangent let us calculate angles, which is a lot of cool stuff that we need for switching operating systems, for switching coordinate systems, and doing like other shape-based calculations. And oscillation is everything that has to do with like waves, and we can manipulate the different properties of oscillation for animation or other kinds of shapes. There's a bunch of resources that you can read up on. This is made up of the Book of Shaders, Nature of Code, OpenGL, and of like Joseph Wilk, who was the reason why I first looked into shader programming at all. I'm Lisa, and you can like find these lines online or come talk to me afterwards. And this is it. Yeah.